So today is new content. I'm going to go over some data hazards, pipeline processors. And again, this is not on your exam on Wednesday. We already covered what is pipeline, how it's an improvement over single cycle designs, and we've gone over the pipeline data path. And we've also talked about pipeline control. And this is the start of hazards and dependencies. We're going to be covering data hazards. We'll talk about structural hazards, but we're not going to cover structural hazards in detail. So structural hazards. This is a hazard that occurs when you attempt to use the same resource by two different stages at the same time. So example of this would be if you had a unified memory. So in all of our data paths so far, we've seen instruction memory and data memory as separate entities. But if you had it unified together, then in instruction fetch and in the memory stage, you would be conflicting for the use of the memory. And this is more of a problem when you have things like support for floating points multiply, floating points add, where you're going to have that coprocessor on the side and you have multiple instructions waiting for it. So that's where a structural hazard would come in. And that's kind of also the reason that we don't cover this in detail, because we're not covering those instructions in our data path. But data hazards, we will have these and we will cover these in detail. This is occurring when you attempt to use an item before it is written. So if an instruction depends on a previous instruction that hasn't written back its results yet. And then control hazards is when you're attempting to make a decision before the condition is evaluated. So the example here is for branching. Okay? If I have a branch instruction, I don't resolve until the mem stage, currently. So how do I know what instructions should have been done beforehand? Right. So this is our example of structural hazards. Like I talked about, if you have unified memory between data memory and instruction memory, then this load word is trying to access the same resource as this load word. So you would have a hazard. But because we have them separated, we call data memory DM and instruction memory IM, and they are separate entities, then we don't have this structural hazard. So these occur when you have a conflict for use of a resource. And this is what we just talked about. If you have single memory, you have load and stores that require access to that memory, but every single instruction needs to access that memory in instruction fetch too. So in order to allow the load and store to access the memory, if you have this single unified memory, you would have to stall the pipeline and not fetch that instruction. You would fetch it in the next cycle. So it would cause a stall for one cycle. So because of this, to get rid of any of these stallings, because essentially for every single load word or store word, we would have to add an additional cycle of stalling. That's why we have in the pipeline data path separate instruction and data memory. Now with separate instruction and data memories, we never have to do this stall. Okay. Right, so next are data hazards. So read after write. This is a true data dependency, and this would cause a data hazard because this add instruction is going to write to register 3, and it's not going to have the new value of register 3 until what cycle?
For read.
After execute, okay? That's when we actually have the new value of 3, which is register 10 plus register 11. Okay? But this sub is trying to read the value of register 3 in which cycle?
Decode.
It's decode, which is third cycle. Right? So we have this dependency. We have to stall the sub instruction until we can get the data from the add instruction to the decode stage of the sub instruction. And if we didn't do that, then subtract would use the old value of register 3 instead of the new one, and our resulting implementation of the data path would be incorrect, right? We wouldn't get the expected results for programs. All right, so write after write. So in this case, for our simplified pipelining, write after write is not a problem. Okay? We do in order execution. There is no way that an instruction can finish before another instruction has finished ahead of it. But with what you guys will learn about in your research projects, and I'll also talk about it a little bit, is there's this possibility of out of order execution. And in out of order execution, having this write after write, we have to make sure that if this subtract is finishing before this add, that's normal execution, right? Well, after the add. But let's say that the subtract finishes first, and then there's some instructions in between this add and the subtract that are using register 3. If they use the register 3 that sub wrote, then we would have the wrong results. So we have to keep track of these things in out of order execution to make sure that we're giving the instructions that are in between these write after write dependencies the correct register values that they're expecting. And the other thing that you can do is you can just delay these instructions. And then right after read, we call this an anti-dependency. Why do we call this an anti-dependency?
Because in the first one, n doesn't change.
10's not changing, right? So there's no real dependency here. So here is our data hazard example. And in this MIPS code, we're highlighting the dependencies. So from this sub to this and, what kind of dependency is it? Well, read after write, yep. What about between this sub and this or?
Still.
Yes. Still read after write. And this sub and this add.
After right.
Cool. This is still read after write. And between the sub and the store word.
Oh.
Yep. This is still read after write. So we don't have problems with all of these instructions, right? Where do we have problems with these instructions? Which instructions are going to have issues?
I think sub and add.
You're talking about the first two?
Mhm.
Does sub really have a problem?
I guess we add the value of register two in add.
Are you talking about and?
Oh, yeah, no, I read that wrong. Never mind.
So what I just wanted to clarify is sub has no problem, right? Sub can execute normally. It's not dependent on anything. Right, the dependency from this and to this sub is the write after read. There wouldn't be really a problem here between going from sub to and we have the read after write. But so we have the problem with the and, right? Because what cycle again do we get the results for register two?
Third cycle.
And what cycle does it get written to the register file?
In the fifth cycle.
And what cycle do we need that value
In
For
the
the-
second cycle.
in the third cycle?
Third cycle.
Right? Because this and doesn't start until the second cycle. But what I also wanted to point out was, does this say add have a real problem here?
No, because by that point, the sub has finished its write back in the
Yeah.
pipeline.
And then the other thing that can happen is if we fix this problem between the sub and the and, then all of the subsequent instructions afterwards, considering that we are doing in order executions, would also have that problem fixed too. Right? So if we ignore it, a couple of these instructions will have problems, but later on it would be resolved. But if we fix it right away, then all of these following instructions will have it resolved as well. Okay. So how are we going to fix this?
Add a register that can store the values and then push it into the other parts of the pipeline earlier.
Do we stall in between sub and end?
You could just.
Yeah, so the very first thing, the simplest thing to do is to solve. Okay? And for your answer, you don't need to add a register because the pipeline register between execute stage and memory stage is going to hold that value already. We just need to add a connection is what we would need to do if we were going to forward. So because this result is needed before it is available and we don't have any forwarding support yet, we need to stop. Right? And then the question is, how many cycles do we need to solve? So we do not write until the fifth stage, right? The fifth cycle. So how many cycles do we need to stall?
And we need the one for and at the third cycle. So three.
Depends how it's implemented, but 2 or 3. So we are going to read the operands in this instruction second stage or the third cycle. And that's when we would figure out, oh, there's an instruction ahead of me that is trying to write to the register that I'm reading from. I should stop. And the reason that we could just stall 2 cycles is that's the cycle that the data is coming back to the register file. So if you have forwarding supported by the register file itself, then it can just let that data flow through. So it'll be at the register file in the 5th cycle. So 2 cycles. And this is our multi-cycle diagram with the arrows showing the forward, like the dependencies. So the same instructions, right? We have all of these dependencies. So if we add those 2 cycles of stall, so 1, 2, right? Shift all of these things to the right by 2 cycles, we solve all of our problems. So here are our solutions for working around these true data dependencies. The first one is, like you mentioned, just stall it. Every time we have this problem, we just look at the register operands of the instructions that are still in the pipeline, look at the registers that we're reading from. Are they the same? If they're the same, stall until we can get that result back. The second solution is a software solution where we say to the compiler, this is our architecture. This is how many stalls we need if we have this dependency. And the compiler would just insert the operations in order to ensure that all of our operands are ready when the instruction is coming into the pipeline. And the third solution is through hardware forwarding. So as soon as the results is available, we send that data to the stage on the pipeline where it's needed. And then the fourth solution is again software, it's code scheduling. So rather than inserting no ops, the compiler's job is to figure out where are some independent instructions that I can execute in the meantime and reorder them such that rather than stalling, I'm actually doing something useful while we wait for the dependent operation to finish. So here is solution 1, pipeline stall. And again, we have this read after write. So we need to stall twice. So we have the add fetched, it's decoded, and in this second cycle, we fetch the sub. Okay. And then in the third cycle, the add is executed and we decode the sub. And it's when we're decoding the subtract that we figure out we're trying to read the same operand as the instruction before us is writing to. So when that occurs, then our data path will signal to the pipeline. We need to stall. The sub is going to redo its decode stage. So when it comes to the next cycle, cycle 4, the sub is redoing decode. And then it again sees the add is not done yet. The data is still in the pipeline. It's not back into the register file yet. So I'm going to redo decode again. And then that's where we get here. And now we do decode for the third time. So because we've done it 2 extra times, that's 2 stalls, right? Then we see, okay, the data is now in the register file. Like the register file lets me pass it through. So now I can continue with my sub instruction. So I just want to be clear here that these 2 stalls, we don't actually do instruction fetch here, right? We don't know we have a problem until cycle 3.
So we fetch when the first pipeline is decoding.
Yeah.
And then we
Yeah.
just keep stalling on the decode.
Yeah.
Okay.
So when you're drawing these multi-cycle diagrams, what I don't want to see is that's because we have the foresight, right? I can see that we have this dependency. I know we need to stall twice. So I just put these levels in, right? But what I want you to think about when you're drawing these diagrams is what is actually happening in the hardware on the fly. The second cycle, we still fetch the sub. The third cycle is where we find the problem. We redo decode in the fourth cycle. And we still have a problem, we redo decode in the fifth cycle. And now our problem is resolved. So this diagram is just from the textbook, but I have examples of how we're expecting you to draw these diagrams based on what is exactly happening in hardware every single cycle on campus. So when you see these dependencies, do not just draw bubbles like this. This is more indicative of the second solution of inserting no ops, right? Because this would actually be a no op, this would actually be a no op. Then we actually fetch here. If these were no ops, then we would fetch here, right? But they're not no ops. This is the pipeline stuff. Is that clear for you guys? So the software solution. We want to have this compiler guarantee that there's no hazards, right? So where do we need to insert these no ops? Do we have any dependencies between the sub and the and? Yes, where are they? Just which word is your number?
This was right back in the decode.
Register 2. What about between and or? No problem, right? Or an add. No. And then add and store word. No. But sub and add and or and add and store word. But if we solve the problem for sub and, we will subsequently solve the problem for all instructions afterwards, right? So we're going to insert two no ops between the sub and the and. Right? That's what our compiler would do. And then our data path can be simpler. We don't have to do any hazard detection, but it's still worse performance than some of these other solutions that we're going to talk about. But this is identical performance as just stalling the pipeline. The same thing. It's just where are we solving the problem? Are we solving the problem on the fly in the hardware? Or are we solving the problem during violation of the code before it even gets loaded into hardware? So both of these solutions slow us down, right? So like just say that 20% of our instructions have dependencies. And that's pretty generous. I mean, usually sequential code, right? We're doing things one thing after another. They're going to be dependent on each other. Then 20% of our program is now having a CPI of essentially 3 rather than 1. So that would negatively impact our performance. So we will talk more about these other solutions, which are hardware forwarding and code scheduling. These will give us better performance while solving our problems. So, solution 3, forwarding. So we want to use the results once it's computed. Don't wait for it to be stored in the register file. Just forward it from one stage to another when it's ready. So this requires extra connections in the data path. And also we have to do the on-the-fly version. The software will not do this for us. You can't just tell the compiler about this. This will have to be done in hardware, but we can do this. So here's our example. We have the add instruction, and the sub instruction is dependent, right? And we have the result from the execute stage stored in the register here between executes and memory, right? So then at the beginning of cycle 4, I take that result from this register and forward it to my execute phase. So rather than using the data that I read from the register file, I throw that away and I use the correct data from the results of the add instruction. So what are we going to add to our data path in order to support this? What am I doing here essentially?
You're checking if registers are the same.
Yeah, but in terms of what is being input into the first operand.
The results of the ALU from the execute.
So I'm making a choice.
Yeah,
Right.
okay, I'm looking at it.
So if I'm making a choice, what does that mean in hardware that I need?
Flux.
I need a mux. Okay. So we're going to insert a mux before the inputs of the execute stage. Right? We already had a mux down here. And we're showing that we need a mux for forwarding for the first operand. Do we still need to expand the mux for the second operand?
Not anymore.
I would think so, because if
Mhm.
it's the other register, you still need to be able to choose between that register or the ALU and the
Yeah,
previews.
so in this case, no, right? Because in this case, our dependency is on that first operand. But there's nothing to stop it from being on the second operand, like you're saying. So we need to also expand this mux down here. So we need, for the second operand, we need to be able to choose between the data from the register file, the sign extend intermediate, or the forwarded operand. And in the first operand, it's just data from the register file, forwarded off. Okay. So that's how we're going to implement this forwarding. So now if we have forwarding, and this is our instructions, then we don't have any stalls. I can forward the result of this sub to this, and from the pipeline register to the first operand of the ALU. And then I still have this dependency for the OR because I'm not done yet. So again, I'm just going to forward the result from this register to the second operand. Right? So really the mux for the first operand of the ALU needs to make more than what we just described, right? Should be data from the register file, forwarded from the executes and memory register, or forwarded from the executes and write back the register. So we need to make 3 choices. Choose 1 from 3, and then for the second operand, we need to choose 1 from 4. So we have all those same choices, but also the sign extended immediately. And then all these other instructions don't have the problem because we have written to the register file, right? So now for our type instructions, if we implement forwarding for our pipeline, we don't stall, right? There's no reason to stall. And then this is just asking, how do we detect when to forward? So we kind of talked about this already, right? When I'm in decode, I'm checking my operands with the operands or the destination operand of the instructions in front of me. And we have those stored in the registers, right? And if I can't do forwarding, I stop. But if I can do forwarding, it's not a hazard. I just need to, in the execute stage, check. Okay, this is the data that I want, register 2. I have the data from register 2, but let me check now, does this register 2 match the destination register of the 2 instructions in front of me? It does match. Let me take that instead, right? So we'll compute some additional control signals in these stages. And then the other question that might arise is, what if I have register, I'm trying to read from register 2, and I need to execute, but there's 2 instructions in front of me, and let's just go with this order. So register 2, and let's say that, so this sub writes to register 2, and this and writes to register 2. Let's just imagine. Then when I'm doing this check, right, I'm going to read register 2. Both of the instructions in front of me, write to register 2. Which one do I take? And by the second, you mean?
And
The newest value, right? All right, so this is our data path with forwarding. So here is our expanded mux, right? And it's making those 3 choices. Is it the data from the register file? Is it the data from, where is this first one? Oh, it's from the forwarding unit. Like, trying to follow.
It's from the very end.
All right, is it the data from memory / write back? Or is it the data from execute memory? Okay, those are our 3 choices. And then we have the same 3 choices, but what's not shown here is our sign extended immediate. Okay. And then this is our forwarding unit. And what is it taking in? We have RS and RT. Basically, what are my 2 operands, right? And then does it match RD from the instruction right ahead of me? Or RD of the instruction 2 instructions ahead of me? And then based on that, we can make this choice. Yes. And the other thing that is in the forwarding unit is that instruction in front of me actually writing to that register, right? is it actually writing? So here is our equation. Right, we need to pass these register numbers along the pipeline. And then the ALU operand register numbers in the execute stage are going to be given by, this is my pipeline register. This is RS, my first operand, RT, my second operand. We have data hazards when the execute and memory register destination is the same as RS or the same as RT, and write back is 1, like it's going to write to register. Or the register between memory and write back, RD, is the same as RS or RT, and it's writing to register. Okay. And that's what it's talking about here, but only if the forwarding instruction will write to a register. If they're not writing to a register, we're not dependent on it, okay? And the other thing is we also want to check if RD for the instruction is not register 0, because if it is register 0, MIPS does not allow you to write to register 0, right? Register 0 is always computer. So here are our conditions as if statements, right? So if we're going to write and the destination is not 0, and the destination is my first operand, then I need to forward from the execute memory. If it's the second operand gets forwarded from execute memory. And then same conditions, just checking the memory write back register instead. Again, for both the first operand and the second operand. So here's our double data hazard that we already talked about, right? So we have this add, they're both writing to register 1. And then this add wants to read from register 1. Which forward are we going to take? From the first add or the second add?
Second add.
Yep, from the second add. So the second add is the one between executes and memory, right? All right, so here is your question for today. Your code is 532. See it on. So, yeah, 532. So do answer this on your own first. And just so that we're clear, without forwarding, no forward. I don't see new answers coming in. Is anyone still thinking about this on their own? Next, we have quite a wide spread of answers, so do talk to the people around you. Hopefully we converge to the right.
Pipeline. It takes, you know, the amount to fill those completes that we're averaging. So it's a 5 stage, so the first one completes at 5, and then the next one completes at 6. And now we have to deal with the data hazards. Which is. So it's about how many bits time is something like this, right? So, yeah, because there's a data dependency of what 2 is. So that takes another 2, so we're at 8, so we go 9, 10, and now we gotta do the same thing. Is there data dependency between and or? Yeah, there seems to be one. There's other data dependency, so we gotta wait for another one. So 12, 13. And add. Oh, this is 4. Is that happening? I think so, because either way you go. Yes, 4. No.
Okay, we just have more movement towards the right answer. Does someone want to tell me how they answered this?
So for sub, you change value of 2. For and, you need to access 2, so you need to add an additional 2 to the count.
What's your original count?
5, then plus 2, then plus 1 because it's the next one. Or since the previous one,
Wait. So what's your original count?
5,
Why is it 5?
because the whole first sub.
Oh, you're talking about just completing sub?
Yeah.
Okay.
And then you need to solve 2 for increasing the count to 3, and 5 plus 3, that would be 8. Then, or you would also need to stall again, making it 11. And then add, you need to stall 1 more time, making it 14.
And by stall 1 more time, you need 2 more cycles.
Yeah.
Alright. So this is correct. And just so that it's clear for everyone, I'm going to do it a different way because what you did is fine and it makes sense to me, but it might not make sense to everyone. So another way to do this, rather than just going 1 by 1, is let's assume that there's no problems. Okay. How many cycles does it take for all 4 of these instructions to finish? Well, the sub finishes in cycle 5. The and would finish in cycle 6. 4 and 7. Add an 8. Right? So we have a base of 8. Then we have 9, 10 because we need to stall twice between this sub and the add. 11, 12 because we need to stall twice between this and this or. And then 13, 14 because we need to stall again twice between this or and add. So that's how we can also get to 14. So this is B. Now, same question with forward. Answer on your own first. see any more answers changing. We don't quite have enough time to do the peer discussion. We are very close to the threshold though. So let's just go over this together. My base before was how many cycles? 8. And now between the sub and the and, I need to forward, right? Does this forwarding cost me any stalling cycles? I forward from the execute memory register to beginning of execute, right? And then the or, I need to forward from the sub as well as the and. Okay? So from the sub, I'm forwarding from between the memory and write back to execute, and then from the and from execute memory to beginning of execute. And again, does this cost me any cycles? No. And then for the last instruction, I need to forward just from the or. Right? And this is from execute memory to beginning of execute. Okay. So I don't need to stall at all. So my base is the same as the actual, which is 8. So this is our result without forwarding, and then with forwarding. All right, so for you to do, Wednesday, we have exam 2. Same rules as exam. For those of you bringing graphing calculators, I expect you to know how to clear the notes. Last time I let you use it, if you didn't know. If you don't know how to clear the notes, you're not using your graphing calculator. It's next time. Okay? So just know how to do that so that you can show me that you cleared the notes. If you're going to use a graphing calculator. If you just bring a scientific calculator, there's nothing to check. Right? There's no notes. You have your front and back sheet paper. Right? 8.5 by 11. And then I will provide you with the mid sheet. Okay. And there is no reading for Friday. Friday we will continue data hazard stuff. The other thing is your next thing to do for the final project, which is again just due on Friday. List your preferences for what order you want to present. And again, just your